talk about some aspects of solar energy. As you can imagine, that's such a vast subject that it will take me a lot longer to talk about all of solar energy. So I'm going to take a couple of topics in there, and I picked them because a couple of students who went from Uni Norte and worked with me for PhD actually worked on those problems. Now, when you talk in general about what we can do with solar energy, well, we can do almost all of our energy needs in one way or another with solar energy, whether it's heating or cooling, daylighting, electricity, fuel production, transportation, desalination, cooking. You can, whatever you can think of, we can do that where energy is needed. And in many cases, it makes sense to do it that way with solar energy. However, we are becoming more and more used to first converting an energy source to electricity and then using electricity for all of our energy needs because it's very convenient to do it that way. So I'm going to focus on just that part of solar energy to produce electricity. And we can do it in two different ways. One is called photovoltaics, that is direct conversion of sunlight to electricity, and the other is indirect, which is solar thermal power conversion, that is converting sunlight to heat, and then from that heat producing electricity like you would do in any thermal power plant. So, as far as photovoltaics is concerned, by the way, in the 1953, 54, a lot of things happened in nuclear power. Well, something very significant happened in solar also in 1954. That was the year that 3 scientists at Bell Labs produced a solar cell with 6% efficiency. So that was the beginning of the development that has come up to this point where we can have multi-megawatt power plants based on photovoltaics, or we can have small ones that run our calculators. So all of that development, not only that, solar cells and panels have been produced that are architectural, so they can be then integrated in buildings in place of some of the other things that we use in buildings. So with all of that development, the deployment of photovoltaics has been increasing at a very fast pace. As you can see over here, that from 2005 to 2015, this is the global photovoltaic deployment, that the year after year, average annual increase has been at 46% per year. In 2016, the total capacity was 303 gigawatts. And with the rate that it's increasing, I would expect that at the end of 2017, it'll be about 400 gigawatts. So we're already reaching where nuclear power is deployed at this point. As far as the other way of producing electricity, solar thermal power, you can see various kinds of solar thermal power plants here. Even in 1990, 354 megawatts capacity existed in California, and by the way, that plant is still operating and still producing electricity. Since that time, as far as solar thermal power is concerned, it did not grow up at the same rate as photovoltaics or wind power. There are a number of reasons for that. That does not mean that it is not an important part. In fact, it is as far as electricity production from solar is concerned, it's even more important, and I will explain that, than the photovoltaics that we have, which is increasing at a very fast pace right now. Now, when it comes to costs, I said that the cell was produced or first developed in 1954. Well, the photovoltaic panels were really produced for the space application, and so in space, cost was not a consideration. In fact, cost of the panels was a very small part of the overall cost in the space race. And so in the 1970s, this is in ballpark numbers, cost of solar panels was in the range of $100 a watt of output. Well, in the 1980s, went down to $30 a watt. In 2003, went down to $3 a watt. 2010, $1.20 a watt. 2012, less than $1 a watt. And today, in wholesale, you can buy solar panels at 50 cents or even less than 50 cents a watt. So that's been the development in this field. Of course, I do want to caution that that is just the cost of the panels. You need the rest of the, or balance of the system also, which adds another $1 to $2 per watt. Okay. So we're moving in the right direction. Costs are coming down to a point where at some locations, some areas, nothing else can compete, not even natural gas can compete with solar. Not at all the places, but some of the places. However, when it comes to photovoltaics, we are pretty much reaching the limit of how low the costs can go when it comes to panels. Now, in the balance of the system, we still can reduce the cost quite a bit. Okay? But in panels, unless we go to entirely different technology, we are almost at the limit. And there is a lot of research going on in other ways of producing solar power also that includes nanoscale antennas and some other concepts. So I'm not going to talk about them today. When it comes to solar thermal power costs, they have been stagnant since 1990. So whatever was the cost in 1990 is the same cost today. There are reasons for that, but the reason is not that the cost cannot come down. The cost can come down to almost the same as wind power, I would say, not the photovoltaic panels. Okay. And one other part is that when we talk about these costs, we don't talk about energy storage cost at all. It's very important to understand that, because solar energy is not a base load energy. It's intermittent. It's available during daytime, not at nighttime. Even during daytime, there are cloudy periods when solar energy is not available. So energy storage is extremely important. So the rest of the presentation that I have, I will focus on just these two parts, the solar thermal power and the energy storage, because those are the areas where we need a lot of research right now. Okay? And those are the areas that happen to be where some of the students that went from this university to work with us for their PhD, that's what they concentrated on. Okay? So when it comes to solar thermal power, we also call it CSP, concentrating solar power. One area where advances are being made and can be made that will reduce the cost of electricity is the thermodynamic cycles. just like in nuclear power or in fossil fuel-based power, it's a thermodynamic cycle that you use to convert that energy to mechanical power and then to electrical power. So, so far in the solar thermal power, we use what is being used conventionally in all of thermal power, which is a steam-based Rankine cycle. So that means we need to go into some other cycles which will give us much higher thermodynamic efficiency. So here I show what is the limit of that efficiency. Carnot cycle is a theoretical cycle. You cannot really do that in practice. But that sort of sets the upper limit that we cannot convert at any efficiency higher than that. In fact, we cannot even convert at that efficiency. So what is the practical limit? It's about maybe 75% of Carnot efficiency. So that's the, let me see if I can, okay. So that's this limit. So right now, we are here with the parabolic troughs. It's about 30% efficiency that we get with the steam Rankine cycle. However, with the power tower, we can go to much higher temperatures. With the parabolic troughs, we normally operate at a temperature of between 300 degrees C to 400 degrees C. With the central receiver tower, we can go to temperatures of 600 degrees C, 1000 degrees C, or even higher if we had the materials that would withstand those temperatures, because the only limitation is the materials, not the technology. So that means we could look into cycles that would utilize those temperatures and produce power at a much higher efficiency. So here, for example, is this supercritical carbon dioxide cycle. Now, steam cycle has a limitation that we can maybe work up to 600 degrees C, probably less than that, but not higher than that because the pressures go extremely high. But with supercritical carbon dioxide, we can go to temperatures higher than that. Okay? So that's a cycle at which we are working right now, and that's a cycle, and I'll show you why it's important, how much it can increase the efficiency. Now, when it comes to power cycles, thermodynamic cycles, let me cover the whole range. For temperatures below 300 degrees C, we have the organic Rankine cycle, okay, which is used in geothermal power. Waste heat from industrial applications. And now we are working on supercritical organic Rankine cycle, which increases the efficiency higher than the normal organic Rankine cycle. Now, temperatures above 600 degrees C is where we would use supercritical carbon dioxide cycles or supercritical carbon dioxide cycles with bottoming cycles. And another area for development of thermodynamic cycles which give us as high an efficiency as we can get is what's called the combined cycles, where power is one output, but you could get more than one output out of that. For example, in areas that require water, and they don't have water, but they have seawater. So you could combine the power cycle and the desalination cycle, and therefore the efficiency you get is not just the power production, but also production of water. Okay? And in my introduction, she said that there's a cycle called the Goswami cycle, and that's where I started that process of combined cycles with more than one output from the cycle, and the cycle I developed would produce power and cooling in the same cycle. And so that was named after me, but that started a development or a trend where people started looking at what else could be combined with a power cycle. So when it comes to supercritical carbon dioxide cycle, it would be used with the central receiver tower, sometimes also called power tower, temperatures of the range of 600 degrees C to 1000 degrees C. Supercritical CO2 is the working fluid. And why it's important and what advantage it gives us? Well, we cannot use steam at temperatures above 600 degrees C. So we got to go to a different fluid. With the supercritical CO2, let me go back. With steam in the cycle, at one point, you have to condense that steam from gas to liquid. And that's where a lot of the energy has to be rejected. That's the major reason for inefficiency of the steam cycle. Now, with the carbon dioxide, if you are operating in the supercritical range, you're not condensing it. And so you don't need to reject as much heat. So then you say, well, if you compress a gas, that requires a lot of energy. But in this case, when you get close to the critical point, still remaining in the supercritical range, the density of carbon dioxide is like the density of a liquid. And therefore, it does not require as much work to compress it as a gas would. So it gives you an advantage of being a gas, but at the same time, advantage of what a liquid would give you in terms of increasing the pressure. So with that, if you calculate the efficiencies, obviously you cannot see this graph, but what it is that with supercritical CO2 cycle, at about 750 degrees C, you can get an efficiency of about 55%. That compared to about 30% that we are getting now with the steam cycle, that's a huge increase. And that's only at 750 degrees C. And what else gives us an efficiency of 55%? Well, the combined cycle based on natural gas. So those plants give you an efficiency slightly higher than 55%, about 58%. But they operate at temperatures of 1100 to 1200 degrees C. In this case, even at 750 degrees C, you can get this kind of efficiency, so this makes a lot of sense. So all of the future work that's going into thermodynamic cycles with the Department of Energy as well as other places is going into supercritical carbon dioxide cycle. Okay, so coming to the next topic, energy storage. As I said before, solar energy is intermittent. It's available only during daytime, but not during nighttime. And there's more, that if solar energy, or for that matter, wind energy, gets up to about 15 to 20% penetration in the grid, that's when the intermittency of the resource becomes a real big problem for the grid. So that makes the grid unstable. So we need to, or we have to have energy storage at that point. Okay? Germany found that out in the last 2-3 years, because there are times when they have power available from the solar power plants and the grid does not want it. And there are other times when the grid needs power and those solar power plants cannot provide that power. So cost-effective energy storage is important, and it is essential for solar energy to become a significant part when I say significant part, that more than about 15% of our energy infrastructure. So energy storage being essential, how can we do energy storage? Well, we have batteries. People are working on supercapacitors, thermal energy storage, pumped hydro. So there are many ways we can do energy storage. But the two ways that we can do right now for solar energy, one is batteries, and the other is thermal energy storage. Okay. Now, batteries cost is about $500 a kilowatt hour electric. The thermal energy storage is in the range of about $50 a kilowatt hour thermal. So battery storage has advantage that even when you need small amount of storage, you can put batteries. Thermal storage would be more applicable to larger scale solar power plants. But the cost being so much lower that it makes a lot of sense when utilities are looking into solar power plants that they look into thermal energy storage. So, as I said, that cost-effective thermal energy storage is essential. There's one other advantage of thermal energy storage. It would be used mostly in the CSP technologies or solar thermal power technologies. But as you can see, if you add storage, you'll be adding cost. There's capital cost of storage. However, even though capital cost of storage is being added, the levelized cost of energy is actually going down. That is because with the thermal energy storage, the investment that you made that you otherwise were only using daytime, now you can use it during nighttime also with the energy storage. So the levelized cost of energy, this is just one example at a very high cost of solar power plant, and cost of solar power plants, even thermal power plants, has come down to where, for example, if you add 12 hours of thermal energy storage, that the levelized cost will come down to about this much. So now the question is, how do we do thermal energy storage? You can do what is called sensible heat storage. This is where you can heat a liquid or you can heat a solid, and as the temperatures range, you are storing energy. Or you can do latent heat storage. That's where you change phase of a material. That is, you heat a material and goes from solid to liquid, it stores latent heat. Or you can do chemical storage, which is thermochemical. That is, in the form, you cause a reaction, which is exothermic reaction. That's when you retrieve heat. And when you store heat, you are doing the endothermic reaction, where you need heat for the reaction to go forward. Okay? So these are the three ways of doing it. At the present time, though, the commercially used thermal energy storage is a 2-tank oil storage or 2-tank molten salt with nitrate salts. Okay. And this is what that would look like. So if this is the solar field and this is the power plant, that you have a hot tank which has the molten salt, and you have a cold tank which has the colder molten salt. So you need to have 2 tanks. This is a sensible heat storage system. So this is the present system. And the cost of the present system is about $40 a kilowatt hour thermal capital cost. If you had a power tower, then it would still be the similar situation, but you would have a hot tank and a cold tank. The two-tank solution with oil has a limitation. That is, you can heat that oil only up to about 400 degrees C. Above that, that oil would start to disintegrate. Okay. So you have a limitation. You cannot go any higher temperature than that. The molten salt, though, you can go to much higher temperatures. However, salts that we use, even when they're solid, they are very corrosive. When they are liquid and they're at high temperature, they are highly corrosive. So they have that disadvantage, and both of these have low energy density and high cost. Okay. So as an alternative to these, we have other concepts that we can use. This PCM storage is storage in a phase change material. That is a material that when you heat, it will go from solid to liquid. And when it does, it stores latent heat, which is extremely high. Okay. And so you can store a lot of heat in it. So we focused on this method of thermal energy storage. And we looked at these salts, and this shows how much heat you can store and what are the temperatures at which you would use them. This, for example, looks like very high storage density. These chlorides, these are common materials, like your common salt, table salt, that's sodium chloride. Or what is sold as no salt for people who have high blood pressure, potassium chloride. So that is also a chloride salt, or a mixture of sodium chloride and potassium chloride. Okay. So the point is that you can store a lot of heat in these salts, and these are just common materials, and they are inexpensive. The problem, though, is that they have very low thermal conductivity. And so heat transfer in these salts becomes a problem. And they have corrosion problems, because they're salts. When you take salts to very high temperatures, they will corrode any metals. Okay. So the question was, can we overcome these problems in thermal energy storage? Okay. And so people around the world have been looking into this thing, not now, for the past 20 years. And they've been looking at solutions like putting fins, adding materials which are highly conductive, like graphite, and many other solutions like these, where the objective is how do we increase the heat transfer in those salts. Okay. So we decided not to use any of these, because all of these will increase the cost even more. What did we decide to do? Said, well, let's encapsulate these salts. In other words, we make capsules out of these. If you have to imagine a ping pong ball. So that would be a capsule, and inside that ball would be the salt in which you want to store that energy. Now, because the size is small, the distance for heat transfer is small. Therefore, even though it has low thermal conductivity, it doesn't really matter that much. Okay. It does something more. Now, since you have a capsule, this salt does not come in contact with any of the metallic tanks or any other materials, so you don't have a corrosion problem. So if we could do this, then of course we have a solution. And so this just shows a couple of types of capsules that we made. Before I tell you the full story in it, let me say that our objective was to reduce from the present cost of $40 to less than $15. Okay? This project was funded by the U.S. Department of Energy, ARPA-E, and this was their goal, to reduce the cost to less than $15 a kilowatt hour thermal by 2020. We reduced that in 2015. So these are some of the salts that you can use depending on what temperature you want to use at. You can pick the salt out of these. In fact, we wrote a paper in which we tabulated all kinds of materials that you could use so that you can pick whatever suits your application. Now, as I said that if we could encapsulate, we would solve the problems. We're not the only ones that were looking into it. A lot of people were looking into how to encapsulate these materials. But we wanted to do it with low-cost materials and finding these low-cost coatings that become hard shell. But to do that, there's some major issues. And one issue is that when these salts melt, they expand. The expansion can be as much as 30 to 40%. So if you have a hard shell of a capsule and your salt starts to melt, unless you provide space for melting, that capsule is going to break. So you need to find a method which will allow that expansion to take place. Okay. So if you don't do that, pressure will build up. So we came up with an innovative solution, and that was we applied a coating to this salt. We made a round pellet out of the salt and applied a coating which is flexible, and it has tiny pores so that any air inside, when you heat it, will move out. So we developed that coating, and based on that, we developed this encapsulation procedure. So with that coating, now we start to heat it. So what happens? First, any air in there diffuses out. Then it starts to melt and it expands, so this outer coating expands with it. So now, once it's melted, it's at the final expanded shape. Then when you start to cool it, it starts to solidify from outside in. So as it solidifies, it forms a void at the center. So now you can put a hard shell around it, and when you melt it, it's just going to fill that space, and you won't have any problem of pressure buildup. Okay. So that's how we encapsulated, and this shows example of the these are polymer coated capsules that will work up to 350 degrees C. Then we developed another method of what's called electroless metallization of polymer coating. That means metallizing this polymer so that you get these capsules with metal. And so these capsules will work up to about 450 degrees C. Okay. So now we had these capsules that work up to that temperature. We looked at their cyclic performance, and we did performance for up to about 7 years. And 7 years, no properties changed. The capsules did not leak, the capsules did not break. So we felt that these capsules would work for as long as that solar power plant will work. Okay. So then the next thing we had to do was, how do we do that at high temperatures of 600 degrees C to 1000 degrees C? Okay. Because those are extremely high temperatures. And there the material that we will have to use for the capsule would be a ceramic. Now, going to those high temperatures, we had some other innovations that we put in. These salts that we are using, they are transparent to infrared radiation. Okay. This is something that I had learned back in the 1970s when I was working on a NASA project where we used these salts as infrared windows. So if they're transparent to infrared radiation, you can just add some small materials which are infrared absorbers, and when you do that, you increase the heat transfer in there much higher. So we just did that, and we added some nanomaterials in there, and we found out that we could melt the same material in a time 35% less than when we did not add that material. Okay. So with that, then we started to work on this encapsulation. The major challenges, as I said, requires a ceramic as the outer shell. The problem with using ceramics is that ceramics have to be heated to temperatures of 1200 to 1600 degrees C for them to become non-porous. Okay. And we then asked for help from a ceramics company. In fact, the US Department of Energy gave us some extra money so we could work with Kyocera, which is the largest ceramic company in the world, to work with us to see if with their help, we'll be able to produce these capsules. In the end, though, Kyocera was not able to help. Because even though they have worked with ceramics, they had not worked with this problem. But we were able to take care of that problem, and we were able to make these capsules, and we tested them to more than 1,000 thermal cycles, and there was no change in the properties of these capsules. None of them failed. So we know that these capsules will work as long as the solar thermal power plant will work. So with these developments, what we have been able to do is, this is what the present thermal energy storage is. And this is our thermal energy storage. Not only we don't have two tanks, now we have only one tank. And that one tank is 1/4 of one of these tanks. So with that improvement, what is the current cost as $40 a kilowatt hour thermal? We reduced it down to $15 a kilowatt hour thermal. Okay. So with that, let me summarize and tell you that as far as solar power is concerned, is increasing rapidly around the world. That's because the costs are reducing rapidly. However, as it continues to increase, that when the penetration goes to about 15% to 20%, there will be grid instability unless we put storage in the picture. Okay? And so storage is the key for large-scale penetration of solar power. Okay? Now, thermal energy storage is cost-effective compared to battery storage, because $40 versus $500. However, we reduced that to even lower, $15 a kilowatt hour thermal. And this is something where now the industry is showing a lot of interest to us. So with that, I thank you and open for any questions.